project is a demonstration of a basic machine learning technique called logistic regression. First, we will do part 1, in which we explore the basics of logistic regression by creating a linear decision boundary, and then we'll extend this in part 2 to create more complex decision boundaries. Okay, so first we're going to generate some data.
So we're going to start off with 7,000 examples, and we're going to generate some somewhat random data in 2 classes, and we're going to set the mean and standard deviation for class 0 and the mean and standard deviation for class 1. Then we're going to create a data matrix where we'll store the points in a 2 by n matrix, and another matrix for the labels, which are either 1 or 0. We're going to generate n examples by flipping a coin. So there's a 50% chance that we draw from a normal distribution around distribution 1, and a 50% chance that we draw from a normal distribution around distribution 2. So like we learned in stats class, we can normalize this data by subtracting the median or the mean from each row in our matrix and dividing by the standard deviation. And now we can show the data with colors representing the 2 different distributions.
Okay, so now that we have our data generated, the task that we want to do is to classify red or blue. And obviously this can't be done perfectly, but we will try to make an optimal line to split the data. The way we're going to do this is with a function called the sigmoid function, which is a probability function. Here's a plot of the sigmoid function when evaluated on one variable. And as you can see, it's always bounded by 0 and 1, and it is about 50% at when xt is 0. So we're going to use this model with some parameters to as a decision boundary. This is going to be our decision boundary. How are we going to decide on how good a certain set of parameters is? The way we do this is with our loss function, and the idea of the loss function is we want to take the sum of the actual label times the log of the predicted label plus 1 minus the actual label times the log of 1 minus the predicted label, and then like average that and negate it. To gain some intuition for why this makes sense, here's a plot of what happens when y is 0. If y is, when y is 1. If y is 1, then this thing is 0, and this thing is just a negative log of y hat, so it looks like that. And then here's what happens if instead y is 0. It looks like that. So what this means is if you predict something close to 0, you get no penalty, and if you predict something close to 1, you get a very high penalty. Now the problem is to minimize this function. The way we're going to do this is with this function called LR, logistic regression. It takes in the data and the size of the data, which is n comma m, and what it does is at every iteration, we don't need that many iterations, it will subtract off the derivative. It's going to travel in the direction of the derivative, and we have a derivation for why this is the derivative, which is right here. I won't go through it, but you take the partial with respect to each parameter, and it turns out to be, we can assemble it into a vector like this. You can read it if you want. Okay, so that's our function logistic regression. Let's see what line it generates. So now we generated a line, some parameters theta. We can plot the points and that line. As you can see, our line does a pretty good job of separating between them. How good does it do a job? That's interesting to visualize.
Visualize the uncertainty by making a plot, which we'll show.
We color code it with this new function, color ramp palette, that basically is going to show the color. It shows the probability with a color gradient. Like the stuff that's super blue is being classified as definitely a blue, and then near the boundary it blurs a little bit, the color, because it's less sure. It's making probabilities that are closer to 0.5, and then again it's very certain over here. There's overlap of the data here, so it can't be quite so sure. Yeah.
And now we can show the probabilities sorted in the histograms.
Mm-hmm.
And we can plot the points where we're unsure, and we can see where the program messes up.
Where it's the most unsure, and it is messing up on some of those, based on some of the points are very hard to classify because the two distributions are overlapping. Then we create this cost function. This is the cost function that we talked about before, but now we're going to actually plot contours of it to gain more intuition about how our gradient descent is arriving at the optimal point. This is the contours of the cost function, and in our cost function we actually stored the different values of the parameters. So now we're going to plot those. It started there, it looks like, and then it converged to that center point, which appears to be the minimum of the contours if you look at the lines. And actually we can also draw this as a sequence of vectors, and the sequence of vectors is decreasing in magnitude to 0, so it is converging like we talked about in linear algebra. Okay, so now we're going to do part 2. In part 2, what we want to do is not assume that our data can be specified by a simple linear decision boundary, but we're going to instead try to use a more complicated quadratic boundary. And the process will even generalize to creating arbitrarily complex boundaries. This is probably not desirable, however, because that would mean that you're probably overfitting to your data. But we will make a quadratic model now.
Okay, so first we're going to generate some data that would be better fit with quadratic terms.
And then we're going to plot it. Here's the plot. As you can see, a line is going to do an exceptionally bad job of classifying this data. So let's see what the line will do. It's not going to do a very good job, but let's create the line anyways. Here's the line. As you can see, it's not doing a very good job. There's a ton of green stuff that if we had a more curved decision boundary, we could do better. So instead of that, what we're going to do is we're going to fit a model using not just the linear terms in x, but we actually have x squared terms in x too. And if we also use those, we can train a model with 5 parameters, and it's taking in like the x values, the x squared values, the y values, the y squared values, and it's also taking in this row of 1s so that it can like fit a bias, like shifting. So that model is going to do a lot better than just this line that we have right here. So we're going to fit that model right here, and as you'll notice, we can use the same function, only changing how many rows we have in our matrix. And here's our predictions, and as you can see, this shape looks exactly like what we had before, and we can see where it misclassifies. And as you can see, there's a very small, that blue region that's being misclassified, and that's because we put some noise in the data, so it was impossible to perfectly do it, but it does very good. And that's the essence of this logistic regression technique. You have some cost function that you're trying to minimize, you have some data, and you have labels for it, and you use those data and labels to generate optimal parameters for a model to fit a decision boundary. We hope you use this.